Hi everyone, in today's video we're going to start our discussion on organometallic compounds. In this video we're going to introduce the concept of a metal-carbon bond, and we're going to focus on organolithium compounds, organomagnesium compounds, organocuprates, and then we'll cap it off with an interesting reaction with organozinc compounds. It is my hope that by the end of this video you are able to predict the nucleophilicity of organometallic reagents, prepare and use organolithium and organomagnesium reagents in synthesis, prepare organocuprates reagents, use organocuprate reagents to perform carbon-carbon coupling reactions, then you'll be able to prepare organozinc reagents, and then use organozinc reagents for a special reaction called a cyclopropanation. So, to begin, in order to understand organometallic reagents, we really have to focus on the metal-carbon bond and the electronics around that particular bond in the complex. And for comparison's sake, let's take our methyl chloride with a carbon-chlorine bond. Recall that the carbon-chlorine bond is a polar covalent bond where the electrons are actually distributed towards the chlorine due to the chlorine being more electronegative than the carbon. Now let's compare this to a carbon-lithium bond. The electronic distribution around the carbon-lithium bond is the reverse of a carbon-chlorine bond because the carbon-lithium bond, the lithium, is less electronegative than the carbon, and so electron distribution actually goes towards the carbon in this case. And so as opposed to the methyl chloride, in the organolithium compound, that carbon that is bonded to the lithium is electron dense. And so what I have shown you here is an electronegativity scale that only focuses on some of the more important metals that are used in organometallic complexes. And notice that your metals are all less electronegative than your carbon. And when you start to compare the electronegativity difference between lithium or magnesium and your carbon, you would see that because of that difference in electronegativity, a bond between a lithium and a carbon, for example, actually has a lot more ionic character than a covalent character. So when we see an organolithium compound like the one we're seeing below, we can really think of this molecule as an ionic complex where your carbon has that formal negative charge with a lone pair, and your lithium is more like lithium ions, which once again is supporting this idea that that carbon is electron dense and can behave like an electron dense atom. And likewise, if we were going to ask which of these two organometallic reagents is a stronger nucleophile, what we are really comparing here is the relative polarity of that metal-carbon bond. And so we can evaluate this by looking at the difference in the electronegativity values for zinc and magnesium, and then comparing these values to the electronegativity values for carbon. And here we see that the difference in the electronegativity values for a carbon-magnesium bond is greater than the carbon-zinc bond, which means that the bond dipole moment between a magnesium-carbon bond is actually stronger or more prominent. As a result, the carbon on the organomagnesium compound is going to have more negative charge character, which is going to make it more nucleophilic. Now, let's begin our discussion on organolithium and organomagnesium reagents. So how do we prepare these organometallic complexes? Let's start with our organolithium. If you start with an organohalide, so your X equals to either chlorine, bromine, or iodine, and you treat that organohalide with 2 equivalents of your lithium, you will get your organolithium compound as well as your lithium halide that gets removed as a byproduct of this reaction. Your R group can be an alkyl group, such as in this case, you have your butyl halide. R can also be a vinyl group, and so it could be a halide connected to an sp2 carbon involved in an alkene, and that would still work. You will still form your organolithium compound. R can also be an aryl group, so you can form an aryl lithium compound. So this is a really versatile reaction. Now let's consider your organomagnesium reagent, which, as you can see, it's a little bit different. It's in the form of your R bonded to the magnesium, which is still bonded to a halide, your X. Here, if you have an organohalide and you treat that with magnesium, it has to be in an ether solvent to help stabilize this complex. What you're going to end up forming is the organomagnesium complex, also called a Grignard reagent, where the magnesium has inserted into that RX bond. And here, once again, R could be an alkyl, a vinyl, or an aryl group on your halide. And so once again, similarly to your organolithium, this is a pretty versatile reaction that could form quite a bit of reagents here. Now let's discuss the reactivity of organolithium and organomagnesium reagents. So due to that electron density that is at that carbon when you're bonded to lithium or magnesium, it makes that carbon really electron dense, which means that those carbons are strong bases. For example, if you have methyl magnesium bromide, we are representing this as an ionic interaction rather than a covalent interaction. And if there was even just a little bit of water in your flask that contains this Grignard reagent, we expect an acid-base reaction could occur where our CH3 carbanion can deprotonate our water to form CH4 and our magnesium hydroxide complex as a side product. The pKa of water, which is the acid on the left-hand side of this acid-base equilibrium, is 15.7. The pKa of the alkane that is formed on the right-hand side, which is your conjugate acid of your Grignard, is approximately 50. So due to that significantly large difference in the pKa values, you have the significantly weaker acid on the right-hand side. The equilibrium, if you want to even call it that, is going to significantly favor the right-hand side of this reaction. Which is another way of saying that this is why Grignard reagents do not survive any solution that has even just a little bit of moisture in it or any acidic proton that is on any reactant. So while this creates an issue when it comes to maintaining a Grignard in your solution, as chemists we can actually take advantage of this incredible basicity and install a deuterium onto an alkane or a hydrocarbon. So for example, take your methyl magnesium bromide, this time treated with D2O. Now, just like your water, your Grignard is going to dedeuterate your D2O. Which functionally installs a deuterium on your methane. Okay? And so, Grignard reagents are very basic, but also an organolithium compound. So the same reactivity we expect for organomagnesium, we should expect that for organolithium as well. Organolithium and organomagnesium reagents are also strong nucleophiles, and we have actually seen these reactions in previous videos. And so I'm just going to lay out a summary of the variety of reactions we could expect with these very highly reactive and highly nucleophilic organometallic complexes. We know that if we have an aldehyde or a ketone and we react that with a Grignard, and then do an acid workup, we would end up adding the R group on the Grignard to the carbonyl on that aldehyde or ketone. And our product here would be an alcohol. Grignards can also open up epoxides, which are your three-membered rings with an oxygen on one of the apex points. And we can open that up through an SN2 reaction and then do an acid workup to form an acyclic alcohol. And as a recap of what this mechanism would look like, your R group on your Grignard is your nucleophile, and it would attack one of those carbons on the epoxide and then break apart the CO bond, which gives you your alkoxide, which can then grab a proton from your acid in your acid workup step to ultimately form that product, your alcohol. We've learned that Grignards could react with carbon dioxide to form carboxylic acids. You have to do an acid workup just like before. And so this would be your product of that reaction. Grignards could react with esters. We need excess of our Grignard because we're going to do 2 successive nucleophilic additions to form your alcohols. And here's the product of that reaction. Grignards can react with nitriles. You would form an imine or a deprotonated imine, and then you use H3O plus to hydrolyze that imine back to a ketone, and then here's the product of that reaction. So there's quite a wide array of reactions that Grignards could be engaged in. Essentially, anytime you have an electrophile, a Grignard can attack that electrophile. And lastly, once again, think about the organolithium and the organomagnesium reagents as very similar in reactivity. So all of these reactions that we can do with a Grignard, we can actually do with an organolithium reagent as well. Okay, so now we shift our attention to lithium dialkylcuprates. They're also known as Gilman reagents, and this is the chemical formula, the generic chemical formula for these family of species. We will start with preparing them, and then we will go over to some reactions that these lithium dialkylcuprates can engage in. So the synthesis of lithium dialkylcuprates proceeds through the synthesis of your organolithium reagent. And so you start, once again, with an organohalide. You treat that with 2 equivalents of lithium. Lithium halide leaves the flask, and then you end up with your organolithium species. Your organolithium species can now be treated with 0.5 equivalent or half the equivalent of a copper 1 halide. Once again, another equivalent of lithium halide gets removed from the flask, and then you would end up with your Gilman reagent. So the scope of this reaction is similarly as vast as the scope of preparing organomagnesium and organolithium species, which is to say that you can use an alkyl group for your R, for example, an alkyl halide. You can also use a vinyl group for your R, which like we've seen here with our vinyl halide. And we can use our aryl halide as well in this reaction. So the same scope as our organomagnesium and our organolithium. Okay, so now we're going to focus on the reactivity of lithium dialkylcuprates, and we're going to first review the reactions we have learned about the nucleophilic addition of organocuprates onto carbonyl type molecules. So we know that organocuprates, because they're a little bit weaker of nucleophiles, they're a little bit more selective when it comes to reactions. So as a reminder, if you take an acid chloride and you react that with an organocuprate or lithium dialkylcuprate, instead of getting excessive nucleophilic additions on the acid chloride, you would only get 1 equivalent of the R group onto the acid chloride to form a ketone. We also know that if you have an alpha beta unsaturated ketone or aldehyde, such as what we have right here, and we treat this molecule with a lithium dialkylcuprate, the lithium dialkylcuprate actually serves as a Michael donor. The alpha beta unsaturated ketone serves as a Michael acceptor, And so the nucleophile is going to add on to that beta position of the electrophile to then form your elongated ketone product. And so we end up functionally doing a CC bond formation to form this extended organic compound. So this is our review. So now let's look at a new reaction involving Gilman reagents. This reaction we're going to focus on is the formal coupling of two organohalides together. And this happens when you take a lithium dialkylcuprate, which has its own R group, and an organohalide, which has its own R group. When these reagents react with each other, you form this coupling product where the R group of the lithium dialkylcuprates and the R group of the organohalide come together to form a CC bond and some byproducts that have an organocuprate and a lithium halide that gets sort of washed away. The power of this reaction is the versatility and the robustness of the substrates that you can use. Both are, so the R group that is on the lithium dialkylcuprates and R prime, which is on the organohalide, can be any combination of alkyl groups, vinyl groups, and aryl groups, which means a wide variety of carbon-carbon bonds can be formed. However, let's note here that R prime, so the organohalide, cannot be a tertiary alkyl halide. Okay, so we really want to avoid those in our synthesis because that would not work. It's also challenging to use secondary alkyl halides in this case. Some work, but they're pretty generally ineffective, and so you also really want to avoid those as much as you can. So here's an example that showcases how powerful this reaction is. Here's a lithium dialkylcuprate where the R group is an ethylene R group. And then here's an organohalide where the R group is a phenyl ring. Under these conditions, your coupling will indeed work where now the blue highlighted R group couples to the green highlighted R group at the position where the iodine was in our reactant. We end up forming this molecule, so we can take an sp2 hybridized carbon and actually bond it to another sp2 hybridized carbon to form your carbon-carbon bond forming product. This coupling reaction with organocuprates is stereospecific. This means that the stereochemistry of our reactant controls and is transferred to the stereochemistry of our product. So here is an example of what we mean when we call this reaction stereospecific. So consider this lithium dialkylcuprate. The stereo configuration around those alkene bonds is an E stereo configuration. Then consider this organohalide, which has a Z configuration around the alkene bond. When these two molecules couple to each other, this is what the major product would look like. Note that the stereo configuration that was at the organohalide side is retained. You still have a Z configuration at that particular alkene. And the stereo configuration from the lithium dialkylcuprate is also retained. That has an E configuration around the alkene. And so once again, this means that the reaction is stereospecific because that configuration from the reactant is dictating and controlling the configuration at the product. Okay, so that is your coupling reaction with organocuprates or your lithium dialkylcuprates. Okay, so now we're going to address the Simmons-Smith reaction, and we're going to introduce the concept of a carbene and a carbenoid. And this reaction requires the use of an organozinc compound, and just like your organomagnesium compounds, your Grignard reagents, you can prepare your organozinc compound in much the same way, where you take an alkyl halide, you treat that with a zinc, and then the zinc, just like the magnesium, inserts itself into the alkyl halide carbon halide bond. There is a particularly useful example of an organozinc compound called iodomethyl zinc iodide. To form this important organozinc reagent, you first start by taking diiodomethane, so CH2I2, where you treat iodomethane with zinc in a zinc copper couple, you would form iodomethyl zinc iodide, which once again arises from a bond insertion formally of your zinc into that carbon iodide bond. What we're going to see in the reaction moving forward is that this particular reagent is an excellent source of that CH2 group, where that CH2 group can be transferred onto an alkene in this reaction. So just take note of that highlighted spot on your iodomethyl zinc iodide. So now in the actual Simmons-Smith reaction, if you have an alkene and you treat that alkene with your diiodomethyl, your zinc copper couple in your ether solvent, recall that your diiodomethyl reacting with your zinc copper couple is going to form your iodomethyl zinc iodide, which once again is a source of CH2 in a reaction. The product of this reaction is going to look like this. Okay, so you've essentially formed a cyclopropane ring where the highlighted yellow spot on that ring comes from your diiodomethane. So once again, we've essentially inserted a CH2 group onto a double bond or across a pi bond. This reaction is also stereospecific, whereas if you have a transalkene that you're starting with, treat that transalkene with your Simmons-Smith reaction conditions and reagents, you would form your trans-disubstituted cyclopropane. Okay, and there are two of them because you have a chiral molecule, so the enantiomer is also equally likely to be formed. And likewise, if you had a cis alkene and you treated out under these conditions, you would form a cis disubstituted cyclopropane. Okay, so let's revisit our active reagent. Our iodomethyl zinc iodide, which is formed once again by taking a diiodomethane and you treat it with a zinc copper couple, that is a source of your CH2 group. The CH2 group is called a carbenoid, and the reason why it's called a carbenoid is that it's essentially a source of a carbene-like molecule. So let's think about what a carbene is. So here's a carbene. A carbene is a reactive intermediate. It is short-lived, but it is formally a neutral carbon. So if you look at the formal charge of this particular carbon, that formal charge is 0. So it's a neutral carbon that has 2 sigma bonds and 1 lone pair of electrons. So notice that there is a lone pair at that central carbon right there. It is obviously not very stable, right? It does not have an octet, so it is certainly unstable. However, it is a reactive intermediate that does form, and we can synthesize carbenes in as well to react in organic reactions. So speaking of the synthesis, one way to synthesize a particular carbene is if you start with chloroform or CHCl3 and treat chloroform with a strong base. One example are your alkoxide bases such as tert-butoxide. You get a deprotonation, which then forms this carbanion. And under these conditions, your chlorine on your carbanion can actually leave. So it's a loss of a leaving group. And now you formed your carbene. Once again, these are reactive intermediates that will just end up reacting with something if it can. And so we can actually use, for example, this dichlorocarbene in a similar reaction as we just did for the Simmons-Smith reaction with our carbenoid, iodomethyl zinc iodide. So we can take our dichlorocarbene and insert into a pi bond. like an alkene. So let's look at this reaction as well. So once again, here is our alkene. You treat that alkene with tert butoxide and chloroform. Please remember that once again, the tert butoxide is going to deprotonate the chloroform, and then your chlorine on that particular carbanion is going to leave to form a carbene. And so the reactive intermediate is what I have drawn here, which is your dichlorocarbene. That's the one that's going to insert across the pi bond to form your cyclopropane ring. And so here's the final product of this reaction. Okay? All right, so that is essentially your cyclopropanation reaction. You can do this using your Simmons-Smith cyclopropanation, or you can do this using your dichlorocarbene cyclopropanation, but it's essentially the same idea. You are forming a carbene or a carbenoid, and then that adds on across a double bond, okay? And for both of these reactions, the reaction is stereospecific, and so the stereochemistry of the alkene will map on to the stereochemistry of the cyclopropane. So it's my hope that we're starting to get a sense of how powerful these organometallic reagents are. We can start to think about their nucleophilicity. We can think about how to prepare them, how to use them in synthesis, especially when we start to deal with more interesting carbon-carbon bond forming reactions, such as the one we use with our Lithium Dialkylcuprates, which is this molecule I'm highlighting right here, as well as our cyclopropanation reaction that is essentially gotten from an organozinc compound. And so these are really fun and interesting chemistries that we can start exploring in the future. Thank you so much for watching, and I will see you in class.